Hi everyone, welcome back to the Oracle Chef. In our previous video, we explored Oracle single instance architecture and understood how Oracle processes SQL requests internally using memory structures, background processes, redo generation, and recovery mechanisms. But today we are going to answer a much bigger question. What happens when a single server is no longer enough? What happens when thousands of users connect simultaneously? What happens when one server becomes a bottleneck? And what happens when the business cannot afford downtime? So, this is where Oracle Real Application Clusters or RAC enters the picture. In this video, we will understand how Oracle extends a single instance database into a clustered architecture using multiple servers, shared storage, clusterware, cache fusion, and intelligent workload management. We'll follow the journey from a simple single instance database all the way to a highly available clustered system. So let's begin. Before we understand RAC, let's quickly revisit how a single instance database works. Imagine a user submit a simple SQL statement, select statement from an application. The request first reaches the Oracle listener. The listener does not execute SQL. Think of it as receptionist whose job is simply to accept the request and hand it over to a server process. The server process now begins analyzing the SQL. Oracle performs syntax validation, semantic validation, and object checks before generating a new execution plan. Oracle first checks whether the SQL already exists inside the shared pool. If Oracle finds the SQL in the library cache, it performs a soft parse and reuses the existing execution plan. In many cases, Oracle can satisfy the request without performing additional physical reads. If the SQL is not found, Oracle performs a hard parse. During this process, Oracle evaluates statistics, histograms, cardinality estimates, and optimizer calculations before generating a execution plan. Once the execution plan is ready, Oracle brings the required blocks from data files into buffer cache and executes the statement. Now let's switch from a select statement to an update statement. The blocks brought into buffer cache are modified and become dirty buffers. At this point, the changes exist only in memory. When the user issues a commit, Oracle confirms the transaction, but before those modified blocks are written to data files, Oracle generates redo records. These redo records are stored in the redo buffer. Logwriter then writes these redo records into online redo logs. This is one of the most important principles in Oracle. Redo is written first. Data files are written later. Online redo logs are organized into redo log groups, and each group may contain multiple redo members for redundancy. As transactions continue, Oracle writes redo sequentially. When a log becomes full, a log switch occurs, and Oracle begins writing into the next redo log group. Every committed transaction receives a system change number, commonly called SCN. Think of SCN as Oracle's universal timeline. SCN is crucial for transaction consistency, recovery, operations, RAC synchronization, and even data guard environments. As checkpoints occur, checkpoint information and SCNs are updated into control files and data file headers. Control files are extremely important because they store database metadata, checkpoint information, and redo sequence tracking required during recovery. Meanwhile, ARCN archiver process archives completely online redo logs into archive logs, which can later be used for database recovery. Another important thing to understand is that Log writer and DB writer operate independently. Log writer protects redo, DB writer writes dirty blocks. Oracle does not wait for DB writer to complete before protecting transactions. This architecture is powerful, but it has limitations. We have one server, one memory structure, one buffer cache, one redo stream, one set of background processes. As workload grows, everything depends on the CPU and memory capacity of a single machine. And this is exactly where RAC begins. Oracle RAC was designed to solve these limitations. Instead of one server carrying the entire workload, RAC allows multiple servers to work together as single database. Think of it like replacing a single worker with an entire team. Each node contributes processing power, memory, and resources. At the same time, all nodes access the same database stored in shared storage. A RAC environment requires at least two nodes. Each node contains its own Oracle instance with its own memory and background processes. The nodes communicate through a private interconnect network while sharing storage managed by ASM. If one node becomes overloaded, workload can be distributed. If one node becomes unavailable, surviving nodes can continue servicing requests. This combination of scalability and availability is the core purpose of Oracle RAC. Now, here's one of the biggest misconceptions about RAC. Many people assume RAC shares memory across servers. It does not. Each node has its own SCA, its own PGA, its own buffer cache, its own background process, its own undo tablespace also, and its own redo thread. Each node behaves like an independent Oracle instance. The difference is that all instances cooperate together. Let's talk about undo. Whenever a user modifies data, Oracle stores the before image of those changes inside the undo tablespace. Undo provides read consistency. In if another session requests older committed data, Oracle can reconstruct it using undo information. Undo also plays a critical role during recovery. When an instance crashes, Oracle first rolls forward committed transactions using redo and then rolls back uncommitted transactions using undo. This guarantees consistency. Each RAC node maintains its own undo tablespace. Similarly, each RAC instance generates its own redo stream through its own redo thread. Instead of one redo stream, RAC has multiple redo threads writing to shared SCM, ASM managed storage. And every transaction receives an SCN ensuring all nodes agree on a consistent view of database. Finally, remember this important point. ASM is not a giant hard disk. ASM is an intelligent shared storage architecture that allows multiple RAC instances to safely access the same database files while maintaining consistency and availability. Now let's zoom out and look at RAC as a complete system. Think of RAC as a city. A city needs buildings, roads, communication networks, and administration and traffic management. Similarly, RAC consists of multiple layers of working together. At the top, we have the instance layer where SQL processing happens using memory structures and background processes. Beneath that, we have ASM, which provides the storage layer. Then comes cluster where which manages and monitors the cluster. We also have the cluster registry layer which stores cluster configuration information. Then we have the networking layer responsible for user and node communication. Finally, we have the global coordination layer which ensures every node agrees on the same version of data. Each layer solves a specific problem and together they transform a simple database into a clustered database architecture. Now imagine a user wants to connect to the database. In a single instance environment, the client typically connects directly to a listener. RAC works differently. The user simply provides a scan name. The scan name is resolved through DNS and the connection reaches a scan listener. Think of the scan listener as an airport traffic controller. It decides where incoming connections should land. The scan listener redirects the connection to an available node using a VIP. The VIP forwards the request to the node listener. The node listener establishes the database session. But there is another important concept here called services. Services allow Oracle to intelligently route workloads. For example, OLTP users may connect to one service while reporting users connect to another. The user thinks they are connecting to a database. Oracle is actually deciding the most appropriate destination behind the scenes. This abstraction is one of the reasons RAC can provide both scalability and flexibility. Now we arrive at the heart of RAC, which is cache fusion. This is the future that transformed RAC into a true clustered database. Imagine user 1 connects to a node 1 and executes a query. Oracle brings the required blocks into buffer cache of node 1. Now user 2 connects to node 2 and requests the same data. Before RAC, Oracle would often read the block from disk again. Oracle engineers asked a simple question: why go to disk again when another node already has the block in memory? The question created cache fusion. Node 2 asks the cluster whether another node already owns the required block. GCS, the global cache service, identifies the owner. If node 1 owns the block, LMS transfers it directly across the interconnect, memory to memory, no disk access. Now consider another scenario. User 1 modified data but has not committed. The before image of those changes exists in the undo table space of node 1. Meanwhile, user 2 wants to read the same data. User 2 must not see uncommitted changes. Oracle therefore uses undo information to create a consistent read copy, commonly called a CR block. LMS transfers that CR copy through the interconnect. This is where undo, read consistency, and cache fusion all come together. Without undo, there would be no CR blocks. Without CR blocks, there would be no consistent reads across rack. And this ability to move blocks between memory structures while maintaining consistency is the real beauty of rack. Now let's answer one of the most important rack questions. How does the cluster start? In a single instance database, Oracle reads the SP file, identifies the control files, mounts the database, and opens it. RAC is far more complex. The startup journey begins when the server boots and OHAST starts Oracle High Availability Service daemon and acts as the master coordinator for cluster startup. But OHAST immediately faces a challenge. It needs configuration information. Where does it get the information? The answer is OLR, the Oracle Local Registry. OLR contains node specific resource information required during startup. Without OLR, Oracle would face a chicken and egg problem. Oracle needs cluster information to start resources, but the shared cluster information is stored inside OCR, and OCR itself resides in ASM storage. If ASM is not available, or OCR cannot be accessed. Without OLR, Oracle would not know how to start ASM. The entire startup process would be stuck before it even begins. This is exactly why OLR exists. This is the main question that an interviewer can ask you. Using OLR, Oracle starts ASM. ASM mounts the disk groups. Now OCR becomes accessible. Next, CSSD begins maintaining cluster membership and coordinating node synchronization. Voting disks are used to validate node availability through network and disk heartbeats. CRSD then reads cluster resource information from OCR and begins managing databases, listeners, services, VIPs, and other cluster resources. Only after OCR information is available can Oracle determine which resources should be started. Finally, the database instances come online and RAC services become available for users. What appears as simple startup command is actually a careful orchestrated sequence of dependencies. Now let's see what happens when things go wrong. Because a cluster is only valuable if it is can survive failures. Imagine node 1 suddenly crashes. Perhaps due to a hardware failure, operating system issue, or power outage. The remaining nodes immediately notice that communication has stopped. Oracle continuously exchanges two types of heartbeats: network heartbeat through the interconnect and disk heartbeat through voting disk. When heartbeats disappear, CSSD begins verification. Oracle does not stop immediately assuming failure. It validates the situation using voting disks. If the cluster confirms the node is no longer healthy, Oracle evicts the node from the cluster. Eviction may sound harsh, but it protects the data integrity. The biggest danger is split brain. Split brain occurs when multiple nodes believe they own the same database and begin making independent decisions. To prevent this, Oracle removes the unhealthy node and protects consistency. Data integrity is always more important than keeping every node online. Once the failed node is removed, surviving nodes continue servicing requests and user reconnect through the available services. This is how RAC delivers high availability while protecting consistency. Now let's bring everything together. A user connects through a scan name, DNS resolves the request, and the scan listener redirects the connection to an available node using VIPs and node listeners. The local instance begins executing SQL using its own memory structures and background processes. If required data exists locally, Oracle uses local memory. If another node owns the data, cache fusion transfers blocks across the interconnect. Each node maintains its own undo tablespace and redo thread. Every transaction generates redo. Every commit receives an SCN. Control files maintain checkpoint information and redo sequence tracking. OCR stores cluster configuration. Voting disk maintain cluster membership. CSSD monitors node health. CRSD manages cluster resources. Services distribute workloads. ASM provides shared storage. And together, these components transform a traditional single instance database into a scalable, highly available clustered architecture. This is Oracle RAC, not multiple databases, not multiple copies of data, but multiple Oracle instances working together as a single database. And with that, we have completed our RAC architecture journey. We started with a single instance database. We explored the limitations of running everything on one server. We extended that architecture into a clustered environment. We understood shared storage, clusterware, services, cache fusion, startup dependencies, and failure handling. Most importantly, we saw how Oracle allows multiple servers to behave as one database while maintaining consistency and availability. In the next video, we will go even deeper and open the black box of cache fusion to see exactly how blocks travel between RAC nodes and how GCS and LMS works internally, and why RAC wait events such as GCCR request, GC current request occur. If you found this video useful, please like, share and subscribe to Oracle Chef. and let me know in the comments which Oracle topic you would like to explore next. Thank you for watching, and I will see you in the next video.